Hi all, welcome to your first lecture video for the Calculus 1 class. In this video, I'll just be trying to review several of the concepts that we should know at the beginning of our Calculus 1 class, whether it's precalculus algebra or some trigonometry. Now, because we're reviewing over all of the precalculus algebra and trigonometry, there is no way I can do that in one lecture video. It's completely impossible. So I'm just going to try to hit some highlights. You'll notice several of the assigned homework problems in Achieve are not addressed in this video, and that's done intentionally because I want to be able to cover some things in here and give you other things in the homework that you'll be able to look at on your own. And remember, I'll have videos for every one of those sections of me working out every single problem should you run into any problems as you're trying to do the homework videos. So that'll hopefully address any issues that you have within looking at those. But with what I'm trying to do now is just looking at some of the basic concepts, and everything in this video for sure you should be comfortable with before we start chapter 2, going into limits and the definition of the derivative. Okay, so let me go ahead and pull up my computer screen here. Here we go. And you'll also note, or please also note, that all of these notes that I'm using as far as my videos, these are posted online. I scan a PDF and post it there, so there's no need for you to have to write stuff down unless you just wanted to. But everything that I do in my videos, I also have posted online, not underlined. Okay, so starting off with our precalculus review, I just want you to first of all think about the different types of polynomial functions and their corresponding graphs. So of course we could have a constant function. Sometimes students don't think of that as a polynomial. They think in order to be a polynomial, you have to have variables in there. That's not true. Y equals 5, that is trivially a polynomial function. But we know it's a polynomial function that is always constant. No matter what the x value is, y is always 5. We represent that with a horizontal line. And that should make sense why it's a horizontal line, because no matter what x is, so that's why there's no constraint on x. It's not mentioned in the formula. So x is irrelevant. Whatever x is, the y value is always 5. So no matter what x is, y is always 5, gives me a horizontal line at y equals 5. And similar for any constant line, it's always going to be a horizontal line. Now, if I look at a linear function, that is when we have the x in there instead of the understood coefficient of x being a 0. If I have mx plus b where m is not 0, say for example, if I have y equals 3x plus 2. Well, if y is equal to 3x plus 2, I know that that means that this line has a y-intercept of 2 and a slope of 3 because the coefficient of x is 3. That slope of 3 means in order to get from one point to the other, I would have to go up 3. And, it should be over 1. I don't know why I put a 2 there. That should be the ordered pair 1, 5. That'll be corrected by the time I post it online. So that's 0, 2, and 1, 5, not 2, 5, unless I guess, I'll do this. I'll correct it by making my function 3 over 2x. Yeah, that's it. That's it. So then my slope is right. It's up 3 over 2. Yay, that fixed it. Looks ugly though. Now, what I'm wanting you to remember about these types of problems in what we're going to be talking about in our class, calculus is going to be the study of rates of change. When you think about the rates of change of these two lines, hopefully you'd say, well, this line, it's called a constant function. It doesn't change. No matter what x does, y is always 5. Well, its derivative, we're going to find out, is 0. Derivative is going to end up being the same thing as the slope of a linear function, and in this case, it would be 0. Now, over here with this y equals, and I'll call it 3 over 2x plus 2, since I graphed it with a slope of 3 over 2, up 3 over 2, I could say, well, this line, no matter where I go on it, the instantaneous rate of change at any point on that line, well, it's always going up 3 over 2, up 3 over 2, forever and ever and ever. We could say the rate of change of that line, or in other words, in our class, we'll call it the derivative. Derivative would be 3 over 2. Now, for quadratic functions, at this point, I just want you to understand that the general equation of a quadratic is ax squared plus bx plus c. That quadratic is going to point down if the leading coefficient is negative, and it's going to point upwards if the leading coefficient is positive. And then for cubic functions, a generic equation of a cubic is ax cubed plus bx squared plus cx plus d. So if that leading coefficient a is positive, then the cubic function starts off at negative infinity and it's going to end up at positive infinity. Starts low, ends high. If the leading coefficient is negative, well, it's the opposite scenario. It's going to start off high, and as x increases, the y value is going to go off towards negative infinity. Now, some generalizations that I want you to be able to make for every single polynomial function in existence. It could be any of these or any higher power of a polynomial. What we know as far as the domain of every single polynomial function in existence is all real numbers. Better written as an interval notation as x equals negative infinity to infinity. Now, the degree of a polynomial, it's simply its highest powered exponent. You'll see I called this a cubic, well, because it's degree 3. It's the highest powered exponent. Quadratic, degree 2, highest powered exponent. Linear, degree 1, highest powered exponent. Now, that highest powered exponent will also give us the degree of the polynomial, and that tells us something about the way a function is shaped. If it has even degree, like our quadratic had up here, but it could also be degree 4, degree 6, degree 8, degree 10, degree 76, any even number as the highest powered term. If it's a positive leading coefficient in front of that, you know the end behavior is going to start upward and end upward. It's going to be pointing up as x goes to negative infinity or as x goes to infinity. Now, the reason I leave a gap here is because unlike y equals just x squared, it could have some turning points depending upon what its degree is, but if it's even, it's going to start high and it's going to end high if it has a positive leading coefficient. If it has a negative leading coefficient, well, that even function is going to start downward and end downward. Again, you could have a bunch of turning points in between, but this would be the end behavior. The end behavior of any odd function, I just think of it as a cube, just like up here where I said, well, what if the leading coefficient is positive? It starts low, ends high. Now, instead of connecting, I disconnect this to show it could have a bunch of turning points in between. But if it's any odd degree, like if this were x to the 71st power, you could have as many as 70 turning points in between there. But you know, if it's a positive x to the 71st, it's going to start low, it's going to finish high. For any negative leading coefficient in front of an odd function, it's going to start high, finish low. Now, I was talking about the turning points by saying if it's an x to the 71st degree, you could have as many as 70 turning points. Well, the absolute most number of turning points is always one less than the degree. Now, it could be any even number less than that. So if you have a function, let's say degree 13, how many turning points could it have? Well, it could have 12. That's the maximum number. But it could also have 10. It could have 8. It could have 6. It could have 4. It could have 2. It could have 0 turning points. Like just y equals x to the 13th would have 0 turning points. It'd look very similar to y equals x cubed, just going through, flattening out at the origin, and then going back up. Now, if we talk about, when we talk about the degree of a polynomial, and we just say it's the highest powered exponent, but now when I talk about even and odd functions in general, I'm talking about outside, even broader than exponents. If a function is said to be even, then yeah, every power inside of it is going to be even if it's a polynomial function. But we could also say it's even because you can plug a negative in for x, and it doesn't change the y value. F of negative x is equal to f of x. Now, I showed that down here on the graph of y equals x squared because it doesn't matter if you plug a -2 or a 2 into y equals x squared. F of -2 or f of 2 is going to give you 4 in this case. So you say, okay, yeah, f of negative x is the same thing as f of x. This is an even function. Now, even functions are always symmetric with respect to the y-axis. And then if we talk about odd functions would be like the polynomial y equals x cubed. And you can say, how do I find any odd functions, whether it's a polynomial or anything else? And the way that you do that is you plug in a negative x again. But when you plug in a negative for the x value, it's going to change the sign of the whole function. For example, if you said, well, the ordered pair 2, 8 is on y equals x cubed because 2 cubed is 8. Well, what if you plugged a -2 in? -2 to the third power is -8. So f of negative x is the negative of f of x. You change the sign on x, it changes the sign on y. Now, all odd functions are going to be symmetric with respect to the origin. What you see happens in quadrant 1 will be equal and opposite to what happens in quadrant 3. If you saw something happen in quadrant 2, you would see that equal and opposite happen in quadrant 4. Now, up next here, when we talk about rational functions is just when we divide a polynomial by another polynomial. And what we know about rational functions is that they only exist when their denominator is not equal to 0. Any value that causes the denominator to equal 0 will cause the rational function to not exist. So we have to restrict those from our denominator. Now, the vertical asymptotes are usually going to be at those values that cause the denominator equal to 0, and I'll say they are at those values unless the factor causing the 0 reduces down. Like, let's say you have a factor of x minus 5 in the denominator, and that would create a vertical asymptote at x equals 5. Well, if you had a factor of x minus 5 in the numerator that canceled it out, then you're not going to have a vertical asymptote at 5. You just have a hole in the graph at 5. So I'll say vertical asymptote is when the denominators are 0 after the function is reduced. So any common factors in the numerator and denominator need to be canceled out first before considering vertical asymptotes. Now, as far as horizontal or slant asymptotes, you're going to have horizontal asymptotes in the first two cases here. If the degree of the numerator is less than the degree of the denominator, you're going to have a horizontal asymptote at y equals 0. I put an example over here. I said, well, what if f of x is equal to 5x squared over 3x squared plus 2x minus 8? Please notice, degree of the numerator is 1, degree of the denominator is 2. Every single solitary time the degree of the numerator is less than the degree of the denominator, then you're going to have a horizontal asymptote at 0. It's not just unique to that problem. Every time the degree of the denominator exceeds that of the numerator, then you're going to have a horizontal asymptote at y equals 0. Now, notice my next example here. I'm saying, well, what if the degree of the numerator is equal to the degree of the denominator? My rule over here says you're going to have a horizontal asymptote at y equals the fraction of the leading coefficients. What do I mean by that? Well, over here in my example, I think you can tell what I mean. I have g of x is equal to 5x squared over 3x squared plus 2x minus 8. Okay, so if I want to find out its horizontal asymptotes, I look and I can see, well, the numerator and denominator have the exact same degree. So all I would have to do there is to go in and say the fraction of the leading coefficients here, I have a 5 as the leading coefficient in the numerator, 3 in the denominator. Fraction of leading coefficient is going to be y equals 5 over 3. That will be the line that the y values are going to approach as x gets large or as x gets small towards negative infinity. The y values are guaranteed to get closer and closer and closer to 5/3. And the reason for that is because the rest of the terms end up not mattering. Because if you're at a million, this first term here is a million times the size of the second term, which is again a million times the size of that term. So you can say, wow, okay, as x gets large, this problem really reduces down to just that right there. And you can say, as it reduces down to that, you can see that the y value is going to go to 5/3. Now, in the scenario where we have no horizontal asymptote is what happens when the numerator is of greater degree than the denominator? Well, you're not going to have a horizontal asymptote. Now, you will have a slant asymptote if the degree difference is just 1. So if the numerator is degree 3 and your denominator is degree 2, sure, you're going to have a slant asymptote. But what if the numerator is more than 1 degree greater than the denominator? Well, then it's going to reduce down to something that's not just a line, so it wouldn't be a slant asymptote. It might be a quadratic asymptote, a cubic asymptote, or something like that. The only ones we really think about and help draw out our rational functions is if there's a slant asymptote. So that's why I said a slant asymptote may exist. They'll only exist if the degree difference is just 1. Now, looking at a couple of examples here. I give you the rational function x plus 3 over x minus 5. First of all, the domain. You say, well, clearly this rational function is not going to exist if that denominator is 0. Well, that tells me that x cannot equal 5. Well, the domain in interval notation is the values that x can be. So you'd say negative infinity to 5, union 5 to infinity. The vertical asymptote exists at any of those values that cause the function to not exist, as long as the factors that cause those values that not exist don't cancel with the numerator. Well, clearly x minus 5 is not factoring out in this expression. So I can say, well, I will have a vertical asymptote at the restricted value of 5. So you'll see over here, I went ahead and drew in a vertical asymptote in my graph. And then the horizontal or slant asymptote, degree of the numerator and denominator is the same. So y equals the fraction of the leading coefficients is my horizontal asymptote. Horizontal asymptote in this case is just an understood 1 since each of my leading coefficients are 1. Now, before I think about my graph over here, I wanted to go ahead and plot out the x-intercept and y-intercept. We know the x-intercept occurs whenever y is 0. So if you set this rational function equal to 0, and what I need you to remember, anytime you set a rational function equal to 0, the denominator becomes irrelevant. The only thing that can make a fraction 0 is the numerator of the fraction. Now you can algebraically show yourself that by saying, well, how would you get rid of x minus 5? You'd multiply it on both sides. If you multiply 0 by x minus 5, you still get a 0. So now we can see, okay, the only x-intercepts are going to be when 0 is equal to x plus 3, which gives me an x-intercept at negative 3. My y-intercept, anytime you're wanting a y-intercept, you just say, well, that's when the x value is 0. Plug a 0 in for your two x terms, and you'll just get y equals 3 over negative 5, which is negative 3/5. You'll see I plotted out the y-intercept over here. Now, soon as I plotted in these 2 points and I knew that this was my horizontal asymptote and I knew that this was my vertical asymptote, it's an extremely easy graph to draw. I know as x goes towards negative infinities, the y values had to approach that horizontal asymptote. Excuse me. As x approaches any vertical asymptote, you know the y values will go off to infinity or negative infinity. Well, you don't have another x-intercept or anything, so the only option as you approach this vertical asymptote from the left is to go down towards negative infinity. So as x approaches 5 from the left, the y value is going to go off towards negative infinity in this direction. Now, on the other side, and you'll notice I didn't plot a point or anything, I just knew it. And I would rather you just know it too. How did I know it? Well, because the factor that calls the vertical asymptote at 5 is x minus 5. Look at the power on x minus 5. It's an odd power. It's to the first power. Anytime the factor that's causing the asymptote is to an odd power, you're always going to have opposite behavior on each side of the asymptote. Now, what if that was x minus 5 squared? I promise you, You're to have both sides doing the exact same thing, that either both go down or both go up. But in this case, it's an odd power, so as soon as I knew this part looked like that, I knew the other part looked like that up there. Now, if you wanted to, you could have plotted out, say, an x value of 6 and said, well, if x is 6, your y value is going to be 9 over 1. You'd have the ordered pair 6, 9, which then from that point you could easily say, yep, that's going to be that portion up there. Now, if I just ask you for equations of asymptotes here, I say determine the asymptotes horizontal, vertical, horizontal, or slant. So if I look at this first one, now one thing I missed here is I didn't stipulate the vertical asymptotes. Vertical asymptotes would exist whenever the denominator is 0. This would have vertical asymptotes at positive and negative 3, because x squared minus 9 factors to x plus 3, x minus 3, set each of those factors equal to 0, you'll get your 3 and negative 3. Well, I should say x equals 3 and x equals negative 3 is your two vertical asymptotes of this one. Now the horizontal asymptote, you just say degree of the denominator exceeds that of the numerator, therefore your horizontal asymptote is y equals 0. Now over here, I have the degree of the numerator exceeds the denominator, so I know I will not have a horizontal asymptote, but I will have a slant asymptote. I find the slant asymptote by long division, or you could have also used synthetic division. So I used long division here. I divided x minus 5 into x squared minus 6x plus 7. I said x times x will give me x squared, x times x, x squared, x times negative 5 minus 5x. Now, please remember you always have to subtract that region out. So you say, well, that's where my x squareds cancel. Negative 6x plus 5x still gives me minus x, and then I bring down the plus 7. Now I know x times negative 1 will give me that negative x, so I multiply by negative 1, I get negative x, and then I would have plus 5. We subtract out that group. The negative x's cancel, 7 minus 5 gives me 2. So I know that if I used long division to divide the denominator into the numerator, g of x is equal to x minus 1 plus 2 over x minus 5. Now, the slant asymptote is asking you to think about what happens as x gets large. Well, what happens as x gets large, this is still going to be x, that's still going to be minus 1. However, as x gets large, 2 divided by some increasingly large number goes off towards 0. So for the slant asymptote, you always just ignore any remainder, because as x gets large, that remainder becomes irrelevant. And you say, well, okay, the slant asymptote is just y equals x minus 1. And I didn't mention the vertical asymptote. You would have a vertical asymptote, same thing as in this problem up here, of course, at x equals 5. Now, next page. First thing I wanted to mention here is a bit of mathematical shorthand notation. I need you to see anytime you see this backwards capital E, that's mathematical notation for there exists. So if I say in order for a function f of x to have an inverse, it must be 1-to-1. Well, okay, what does a 1-to-1 function mean? And it means, first of all, the definition of a function, for every x, there exists one y. And then I can say, well, all right, but what part of this makes it a 1-to-1 function? It's because that relationship is a two-way street. Yes, for every x, there exists only one y, but for every y, there exists one x. So when we think about a 1-to-1 function, it's got to pass both the vertical and horizontal line test in order to be a function. That's invertible. Now, when I talk about the inverse of a function, we're always going to denote it with a notation. It looks like f to the -1 power of x. It's not the -1 power. This is read as f inverse of x. And so I put over here in red, please note, f inverse of x, it is not the multiplicative reciprocal of f of x. It does not equal, oh, I'm just dividing by f of x. Nope, It's not equal to 1 over f of x. Well, how would I write 1 over f of x without putting it in that fraction? I would have to put it as the group f of x and put parentheses around the entire group raised to the -1 power in order to represent this. But anytime you see that -1 like this, it means the inverse of a function. Now, the inverse of a function isn't simply dividing by that function, because the goal of an inverse is to undo the original function. That's what I said down here. The purpose of an inverse function is to undo an original function. Now, let's go ahead and talk about two obvious inverses here. If I have f of x is equal to x cubed, I can say, okay, so for every x value, the y value is going to be that x value cubed. It's going to take x and turn it in the y values into an x cubed term. So it's going to cube all of them. Well, the inverse of that clearly is the cube root function. But to show that, I just say, well, in my original function, I would have y is equal to x cubed, f of x being y. And now, whenever I'm trying to find the inverse of a function, I know the inverse of a function always flips the ordered pairs. If the original takes x to y, the inverse has to take y back to x. So I can say, well, then flip the variables. X equals y cubed. Now, solve for the new y. Well, take the cube root of both sides. Y equals the cube root of x. We can easily say the f inverse of x is the cube root of x. Pretty simple. Now, what if I have something like h of x is equal to x squared, and I accidentally put f inverse instead of h inverse, but that's no big deal. So if I have f of x or h of x here is equal to x squared, you'll see over here I said you must restrict it. Why must you restrict it? Because y equals x squared is not a one-to-one function. If you tried to take the inverse of it as is, it's the inverse of a parabola, which is like a u. Well, the inverse is going to look kind of like a C, or it's better thinking of as a sideways U, starting at the origin, pointing up and down as it moves to the right. You'd say, well, what's the problem with that? The problem with that is it's not a function. It wouldn't pass the vertical line test. So would it have an inverse? Yes, but it wouldn't have an inverse function. The nice thing about working with functions is we always want to have a reliable, predictable output for every input that we put in. So I can say, well, all right, if I need to restrict it to where its inverse is a function, then the original has to be one-to-one. You can easily do that by just saying, well, what if I restrict x to be values greater than or equal to 0? Then it's just the right-hand portion of the original parabola. You can say, yeah, that part will have an inverse. So y equals x squared with this restriction. So when you take the inverse, you say, well, I'm going to flip the x and y values, solve for the new y by taking the square root of each side. Now, from this step to this step, I'm wanting you to initially think, ooh, he forgot something. Whenever you're taking the square root of both sides, you're supposed to say the positive or negative root of the side not containing the variable you're solving for. So normally we would put y equals positive or negative root of x. I don't in this case. The reason I don't is because I know that the domain of the original problem had to be positive numbers or 0. So that means the range of my answer has to be positive numbers or 0. So I know y can only be 0 or positive numbers. Well, the square root of x can only be 0 or positive numbers. It's 0 when x is 0. It's positive when x is any positive number. And it's undefined when x is negative. So I can say, yes, okay, then the inverse of this function is simply just the root of x. Now, going back to what I was talking about right here, when I knew that the range of my answer had to be positive values only, well, the reason is because the domain of your original function is always the range of your inverse function. The y values, or the range of your original function, always form the domain of your inverse function. And if you're talking about their graph symmetry, they're always symmetric about the line y equals x. Now, seeing an example with that, and I wish I'd drawn them out on the same graph. You could have saw a little more easily that they're symmetric about the line y equals x. But over here, if I'm looking at this one, clearly it has a domain starting abruptly at -6. It's not defined until x is -6 and then going off to infinity. So the x values range from -6 to infinity, including -6. The y values are going to start at -infinity and go up to and include 0. So y is equal to parentheses -infinity to 0. Now, without even thinking and without even graphing this, I know the domain of the inverse has to go -infinity to 0. The range of the inverse has to be -6 to infinity. Now, plotting these 2 points, if the original function takes -6 to 0, the inverse has to take 0 back to -6. So this x-intercept becomes a y-intercept on its inverse, and I can say, well, that's where the ordered pair 0, -6 comes from. The original had the ordered pair 0, -4. Its inverse has to have the point -4, 0. And then the original function moves to the right and down. Well, its inverse is going to move to the left and up. And I can say it starts at the very end, it starts to move down more quickly. Same thing here, it starts to move up and to the left more rapidly up here. So I can say, okay, this pretty nice function in this case. Exponential and logarithms. The main reason we talk about inverse functions is in order to work with exponential and logarithms. They are our most important inverses of one another. Now, whether you're talking about an exponential base A or a log base A, I want to make sure that you understand whenever we say exponential functions have a domain that goes from -infinity to infinity, sometimes people mistakenly think that that means the exponential base can be any number from -infinity to infinity. That's not the case. While that exponent can be anything it wants to be, that base A has to be a positive number. It cannot be 0. It cannot be negative. And the only reason we trivially say it cannot be 1, because if it's 1, it's not an exponential function. 1 to any power is always 1. If y equals 1 to any power, it's just a horizontal line. But in this case, as long as a is not 0 and as long as it's not equal to 1, then we can say, yeah, it's an exponential function. And it's also valid for any log. So you don't want a negative value in your log, you don't want a 0 in your log base, and you don't want a 1 in your log base. Anything other than that, it's going to be fine. Now, the domain for exponential function goes from -infinity to infinity, the range from 0 to infinity. The intercept, every single solitary exponential function in existence crosses through the point 0, 1, unless it's being vertically shifted, then it might not pass through that point. But in base format, it's passing through the ordered pair 0, 1. And they all asymptotically approach the x-axis, or you can think of it as y equals 0 here. Excuse me. Now, you can see in blue, I've drawn out the generic graph of any exponential function, base A, where A is a positive number greater than 1. So if I'm thinking of this as, let's think of it as 5 to the x. Well, 5 to the 0 is 1. 5 to the first would be 5. 5 to the second would be 25. So you can see it's going to increase really rapidly because that x is the exponent. If it were 5 to the x, by the time x got to 3, your y value would be way up at 125. Now, similarly, in the other direction, if that base A is greater than 1, such as 5, you'd say, well, at -1, it'd be 5 to the -1, it'd be it would be positive 1/5. If x is -2, it'd be 5 to the -2, which is 1 over 25. 5 to the -3 would be 1 over 125. It very rapidly approaches that x-axis, but it can never hit it because it's always going to be 1 divided by some power of a there. Now, again, remember, a has to be some positive number, but there's nothing that says it has to be greater than 1. what if a is some fraction like 1/5, 1/2, or what if it's 0.9? If that, oh, and this should be if the base a, not x there, so this is a. So I'll say if that base a is some number between 0 and 1, then I know that it's going to drop on the right-hand side, because think of it if a was 1/2. If a is 1/2, then 1/2 to the first is 1/2. 1/2 to the second is 1/4. 1/2 to the third is 1/8. It's going to get smaller and smaller and smaller as x grows large. And on the other side, it's going to get larger as x goes to a negative power. For example, 1/2 raised to the -3, that'd be the same thing as 2 to the third. It would be 8. So it's going to get large on that side. And again, remember, that's, I started to call it a typo, but it's an inco since I wrote it. So that needs to be an A there instead of an X. I'll just leave my pen covering that because that's bugging me. Haha. Now, for the other side over here, I can say for logarithmic functions, just as exponential functions always pass through the ordered pair 0, 1, logarithmic functions always pass through the ordered pair 1, 0. And whereas exponential functions, as the x increases, y increases rapidly fast. Well, with logarithmic functions, as x increases, y increases excruciatingly slowly. Its range, it's still going up to infinity, but it does so very, 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 very slowly. And then instead of asymptotically approaching the x-axis, it's going to asymptotically approach the y-axis here. And that's, whenever I think of a logarithmic function, I think of the blue one, because 9 times out of 10, that base a is going to be some number greater than 1. But in the rare cases where you do have a decimal base for your logarithm, you just need to remember, well, that's going to reflect it about the the x-axis, and it's going to end up as x increases, the y is going to go to -infinity slowly, and it's going to asymptotically approach the y-axis as x approaches 0. It's going to go up to +infinity, and now that's if the value of a is some decimal between 0 and 1. Now, up here, I didn't talk about this, but you can see it on the graph. No matter what the base a is, whether it's greater than 1 or if it's a number between 0 and 1, the domain for any logarithm, it's restricted. And it shouldn't come as any surprise that it's restricted, because remember, these two are inverse functions, so they're just flipping the x and y values. So the y values of this graph becomes the x values of this graph. Y values went from 0 to infinity. Well, x values go from 0 to infinity for the logarithm. In the exponential functions, you can plug any value you wanted in for x. So the range for logarithmic functions is going to include every single value for y, from -infinity to infinity, from -infinity to infinity, no matter which type, whether it's a larger than 1 or less than 1. Instead of having a y-intercept, it's impossible for them to have a y-intercept, but they do always have an x-intercept at 1. So exponential functions always have a y-intercept of 1. Logarithmic functions always have an x-intercept at 1. And again, that's unless there's any horizontal or vertical shifting that's going on that could affect it. Now, the vertical asymptote, again, unless it's being shifted, is always going to be your y-axis, just like the x-axis is always the horizontal asymptote for exponential functions. Now, the most popular exponential base is our exponential base E, which is approximately 2.71828. Now, if you wanted to see where E comes from, I put it right here. The formula for E, it's just a limit. It's the limit as x approaches infinity of 1 plus 1 over x raised to the x power. It's the impact of continuously compounding interest. Now, whenever we look at the log inverse of E, well, you just say, well, take the log of that base, which is log base E. But then log base E is rarely written. Normally, we would write it as the natural log. Now, when we talk about working exponential and logarithmic equations. If I say a to the x equals b and I ask you to write that as a logarithm, then I'm wanting you to instantly say, well, no problem. I'd have to get rid of an exponential base a. How do I get rid of an exponential base a? I take the log base a of both sides. Log base a is the inverse of exponential base a. Those a's go a ways, and you're left with x. And on your right-hand side, you'll have the log base a of b. So you say, hey, a to the x is equal to b. It's the same thing as saying x equals log a of b. Now, when you're over here, you should be thinking, this is only asking you, what power do you need to raise a to in order to get to b? And you know the answer is right here. Well, a raised to the x power is b. That's what that's telling you. Now, what if I have b is equal to e to the x? You say, well, I need to get rid of the exponential base e. How do I do that? Well, I take the natural log of both sides. That'd be the natural log of b is going to equal x. Nice. Now, just to reiterate our cancellation properties, this is the same thing I have up here. If you want to get rid of an exponential base a, what do? You take the log base a of both sides, and then you just get x is equal to log base a of b. Well, what if you start with this and you want to get rid of that log base a? And you say, well, the inverse of a log base a is an exponential base a. Sometimes, unfortunately, students think, ooh, I need to multiply by an exponential base a. Absolutely not. The process is called exponentiation. In order to exponentiate each side of your equation with an exponential base a, you literally put both sides of the equation into the exponent of an exponential base a. Now on the left-hand side, it doesn't cancel out. You just get a to the x. On the right, in order to get rid of log base a, I need exponential base a raised to the log base a of b. Then a and log a eliminate each other, and I'm just left with b, and I get a to the x is equal to b. Now, let's use those in some problems here. If I have exponential base 10 raised to the 3x minus 1 is equal to 45, you'd say, okay, so in order to solve that out, I have exponential base 10, so I take log base 10. Now, you don't have to put the base 10. If I would just write log, it automatically implies to be log base 10 since our number system is base 10. I just wanted to make it extremely obvious what I was doing. I'm getting rid of an exponential base 10 by taking log base 10 of both sides. Now on the left, those cancel, and I just get 3x minus 1. On the right, I have the log of 45. Now, I'll want an exact answer and a decimal approximation. So the exact answer here, I solve for x by saying, well, I'll add 1 to both sides. 3x is going to equal the log of 45 plus 1. Then when I solve for x, I'll divide by 3. So I'll get log of 45 plus 1 all over 3. That is your exact answer. If I ask for an exact answer, it has to be that expression. You put that into your calculator, you should get a 0.884. For the next one here we had an exponential, now we have a logarithm. Whether I have an exponential or a logarithm, the first step is always the same. Now I didn't have to worry about it in this one because this exponential, it was already by itself, so I was ready to get rid of it. This logarithm is not by itself. I'm not ready to get rid of it. I have to make sure it's by itself first. So the first step is I'll subtract 20 on both sides. That's what I did here. Then I have 6 times the natural log, so I divided by 6 on both sides. And then you can say, okay, now you've got the natural log by itself. What do you do at this point? You exponentiate with exponential base e to get rid of that natural log. So e and natural log eliminate one another, and it leaves you with 15 minus 7x on the left. But then, of course, you still have that e raised to the 3rd power on the right. Now, again, I want an exact answer, so I can say, well, all right, up next, I'll get rid of the 15. I would do that by subtracting 15 on each side. Then you would have a negative 7x equals this right-hand side. So I can say, well, then x is going to equal what's on the right divided by -7, and that would be an okay answer. I'm not really crazy about the negative in the denominator, so what I'd said is that if e cubed minus 15 over -7 is an answer, a better format of that answer would be positive 15 minus e cubed over a positive 7. You could think of it, all I've done from this step to this step is I've multiplied the numerator and denominator by a -1, and then just instead of writing that as negative e cubed plus 15, it looks better as 15 minus e cubed. Now I can say, well, when I have 15 minus e cubed over 7, I put that into my calculator, I get approximately a -0.727. Change of base formulas that you should be extremely familiar with is that if I have the log of any base a of b, I can either call it the natural log of the number on the end, the natural log of b, divided by the natural log of the base, the natural log of a, or if you don't like the natural log, you can use the common log. You can say it's log base 10 of b over log base 10 of a. It doesn't matter whether you use natural log or common log as long as you're consistent in the numerator and denominator. And then rules of expanding and condensing logarithms that you've got to remember from pre-cal, but it's easy. If you have a product inside of a logarithm, you'll expand that with an addition. If you have a quotient inside of a logarithm, you'll expand that with subtraction. And if you have a power inside of a logarithm, you'll expand that by bringing it out in front and it becoming a constant multiple out in front of the natural log. Now, I know what you're thinking. You're thinking, well, this is pretty good stuff up to this point, but where's the trig? I want to see trig, John. Yep, so do I. So do I. So, your first trig, and I started off with a SOHCAHTOA. So please remember your right trig triangle facts is that sine is the ratio of opposite over hypotenuse, cosine is adjacent over hypotenuse, and tangent is opposite over adjacent. I have our right trig triangle drawn in here with these properties on there, our hypotenuse, our side opposite theta, and our side adjacent to theta. Sine is, again, always the ratio, and you could think of sine as the ratio of vertical over diagonal. It is going to be that, and cosine is always the horizontal over the diagonal. So in this case, the sine is your opposite side divided by your hypotenuse. Cosine is your adjacent side divided by the hypotenuse. And tangent is going to be the ratio of the vertical over the horizontal, or the opposite over the adjacent in this case. We know the reciprocals of those. Reciprocal of sine is cosecant, so it's equal to hypotenuse over opposite. Secant's the reciprocal of cosine, so it's hypotenuse over adjacent. And obviously, cotangent's the reciprocal of tangent, so it's just the ratio of adjacent over opposite. Now, whenever you're talking about the unit circle, sometimes students have a hard time connecting the right trig triangle with the unit circle. It's not that bad. Please remember, unit circle just means that the distance from the center of your circle to any point on the circle has a radial length of 1. That's what it means to be a unit circle. It's a 1 unit circle. Okay, now I also know that if I draw some arbitrary angle t in here to a point on that circle that has this radial distance of 1, and I can say, well, this value t, I could go ahead and create a triangle. Well, I know by definition, the distance you are from the y-axis is always defined to be x. So this horizontal displacement from here to here, certainly x. The distance you are from the y-axis to any point in the plane is, the distance you are from the x-axis to any point in the plane is defined to be y. So this vertical distance I could clearly call y here. So I know that this point in the plane is some arbitrary point x, y. Now I can easily also say, okay, let's make the connection between the sine, the cosine, and the tangent then. Well, up here we know sine is the ratio of opposite over hypotenuse. So if sine is the ratio of opposite over hypotenuse, please look at what the sine of this angle t would be. you'd say, well, the sine of angle T has to be the ratio of opposite over hypotenuse. Ooh, that's y over 1. Well, then that's telling you that the sine is nothing more than the y component on the unit circle. What about the cosine? Cosine's the ratio of adjacent over hypotenuse. This is telling you that the cosine is nothing more than the x component on each ordered pair on our unit circle. And the tangent, opposite over adjacent, it's nothing more than the ratio of the y component divided by the x component of any value on that unit circle. And I keep on talking about values on the unit circle, and I won't go over this since this is a calculus class, but if you're not extremely familiar with this gorgeous unit circle, you need to be. You need to know this right and left, forwards, backwards, coterminal angles of these, and so forth. So like if I said, hey, what is the cosine of negative pi over 3? So, oh, negative pi over 3, that's right here. The cosine at that point going to be 1/2 because the x component is 1/2 at that value. Now, to see how that plays out and what I'm expecting you to know within problems, notice my next page here. So on this next page, I'm saying you'll need the unit circle for various reasons this semester. This should be a very quick and very easy problem. And if I just say something like, hey guys, what's the cosecant of 7 pi over 4? You should immediately, now you wouldn't have to draw it, but you should immediately either draw or else think in your mind, 7 pi over 4, that's just the angle that splits quadrant 4 because it's going to be pi over 4 radians short of a full revolution. And then I can say, what do I know about any angle that splits a quadrant? I know that the x and y component are always the square root of 2 over 2. Now in this case, the x component is a positive square root of 2 over 2, but the y component's a negative square root of 2 over 2 because it's moving downwards. Now, excuse me, that cosecant is the reciprocal of the sine, so I can say cosecant of 7 pi over 4 is 1 over the sine of 7 pi over 4. And I can say, well, I know that the sine of 7 pi over 4 was the negative square root of 2 over 2. So the cosecant at that angle is going to be negative 2 over the root of 2. That's where this came from. And then I can say, well, now I need to simplify that. And the best way to simplify it is to understand that the 2 in your numerator, that's equal to the square root of 2 times the square root of 2. The square root of 2 in the denominator will cancel with one of those, leaving me an answer of the negative root of 2. Now, for this next problem, I have 3 tangent squared x is equal to 1. This is one where I think a lot of people, if they don't have a firm foundation of the unit circle, they would really struggle. So if I'm saying 3 tangent squared x is equal to 1, well, then that's saying, well, tangent squared x is equal to 1/3. Now, if I try to solve for my trig function, I need to take the square root of both sides. So I know that the tangent of x is equal to the positive or negative square root of 1/3. Okay, so that's going to give me plus or minus 1 divided by the root of 3 here. Then I can go over to my unit circle and I'm thinking, all right, I need to know in each quadrant, where is the value at which the tangent is either positive or negative 1 over the root of 3. So here's how I thought of this. I know that this is my numerator, this is my denominator. The square root of 3 is approximately 1.732, and my numerator is just a 1. So tangent's the ratio of sine over cosine or y over x. So whenever you're looking at this, you're saying, well, which one is moving more from the origin? Is it the y or is it the x? Clearly the x is the larger value here. So I'm thinking, what's the only angle in quadrant 1 that I'm supposed to be familiar with in which the x value moves further than the y value moves up? And you say, well, that's at pi over 6. At pi over 6, the x component is the square root of 3 over 2. The y component's 1/2. Please think about the tangent at that value. You'd say, well, tangent's going to be this over this. It's going to be 1 over the root of 3. Pi over 6 is one answer. Now, at which angle in quadrant 2 should you be familiar with where the x moves more than the y? Now, if you're thinking, what does he mean when the x moves more than the y? Well, what about 2 pi over 3? Your x is just moving over to -1/2 there, but the y would move way up to the square root of 3 over 2. Nope, that's not it. It's not going to be at 3 pi over 4 because that's when the x and the y move the exact same amount, the square root of 2 over 2. But at 5 pi over 6, the x component moves the square root of 3 over 2 units to the left, so it becomes a negative square root of 3 over 2, and the y only moves up 1/2 a unit. So I can say, well, at 5 pi over 6, the tangent would be -1 over the root of 3, so I get that solution. And then I'll also get a solution at 7 pi over 6. The tangent's going to be a +1 over root of 3 there. And I'll get a solution at 11 pi over 6 because the tangent at that angle would be -1 over the root of 3. So all 4 of these are angles. Now, if you have a good working knowledge of the unit circle, that problem should be easy. If you don't, you need to make sure you have this absolutely committed to memory to where you're able to answer questions like this second nature. Now, looking at my last one, again, you need to have the unit circle as a second nature. What are we supposed to know about the cosine? Well, the cosine is just the horizontal component on the unit circle. So when I'm asking you a question like, at what interval or intervals make 2 cosine t plus 1 less than or equal to 0? All right, here's what I'm thinking. I'm thinking I need to isolate the trigonometric function. I subtracted 1 on each side to get 2 cosine x has to be less than or equal to -1. Now I divided each side by 2, and I get cosine of t. Sorry, it's not cosine x. Cosine t is less than or equal to -1/2. So t is the angle on the unit circle in which the cosine has to give me a value less than or equal to -1/2. So I literally thought in my mind that this is just this angle t, it's got to make it to where the x component on the unit circle is less than a -1/2. So I was thinking of my unit circle here, and I can say, well, I know x is 0 here, x is positive here, x goes to -1. Well, x equals -1/2 is halfway in between 0 and -1. So right there, I need to find the angles which is going to allow the x value to be less than that. Well, the beginning angle is at 2 pi over 3, because at 2 pi over 3, your cosine is -1/2 and your sine is the square root of 3 over 2. And then you go down to 4 pi over 3, because at 4 pi over 3, again, your cosine is -1/2 and your sine is, in this case, negative square root of 3 over 2. But if I go anywhere to the right of 4 pi over 3, my cosine exceeds -1/2. And if I don't get to quite 2 pi over 3, again, my cosine would be greater than -1/2. So it's only for values in between these two where the x value is more negative than -1/2. Now, since it can equal -1/2, the angles in which the cosine is equal to -1/2 are included. And you'll see my interval notation, bracket 2 pi over 3 to 4 pi over 3 bracket. Just a few other things with trigonometry. You're supposed to be very familiar with both the graph of your sine and cosine function. Here I've just graphed one period of the sine, and then it just continues like that forever and ever. Again, one period of the cosine, and it would continue like this forever and ever. That's why we say both of them have an infinite domain from negative to positive infinity, but they both have a restricted range from -1 to 1. And they both fill their period in 2 pi radians. That's why I just went from 2 pi. Now, on the next page, I'm drawing, or I'm asking you and me to draw a trigonometric function that's undergone some transitions. And so in this one, you say, well, okay, it's still a cosine function, but this cosine function has been horizontally horizontally shrunk, vertically stretched by a factor of 8, and then reflected about the x-axis. Okay, so I need to be able to handle that. No problem. I'm going to reference this graph right here, and I'll say, all right, here's my base cosine function. How does this graph change that base cosine function? Well, first of all, I want to consider what the difference in the cosine of x and the cosine of 10x is. I remember that that's going to affect it horizontally, and whenever something is in with the x, it does the opposite to the x values is what it looks like. A lot of people, if they're not really thinking, they'll say, oh, you're going to take each of your x values, you're going to multiply them by 10. Nope. You're going to divide all of your x values by 10. So please notice, that's the first thing I did. Pi over 2 becomes pi over 20. Pi becomes pi over 10. 3 pi over 2 becomes 3 pi over 20. 2 pi becomes 2 pi over 10, which I wrote as pi over 5. So that's the first thing I did, is I said I'm going to horizontally shrink it by a factor of 10. Now what? You can say stretch it vertically by a factor of 8 and then reflect about the x-axis, or you could just say, well, all that's going to do is it's going to multiply all of your y values by -8. So whenever the y value was 1, now it's going to be down at -8. Whenever the y value was down at -1, it's going to be up at +8. Whenever the y value was up at 1, it's going to be at -8. So all I had to do is say, well, I know the graph of -8 cosine of 10x, it's going to go in increments of pi over 20, and then it's going to start in the opposite direction since it's multiplied by a negative, and then it's stretched by a factor of 8. So I just drew in my cosine function like that. This came from just altering this cosine function. Now, what about the other period? Well, it just continues to look like that. You might also remember the cosine function is an even function, meaning it's symmetric with respect to the y-axis. So f of x and f of -x have the exact same values. I just follow that on along through there. Now, just looking at some other graphs, and you'll notice I don't have anything for us to do. They're already drawn out, both here and in your posted notes online. I'm wanting you to think about the graph of a cosecant function. It's just the reciprocal of the sine. So what I like to do is I like to barely draw in the graph of a sine function and then say, well, wherever the sine function is 0, the cosecant is going to have vertical asymptotes. Whenever the sine function is 1, the cosecant is 1, and then it's going to go off towards infinity as x approaches those asymptotes. Whenever the sine is -1, your cosecant's -1, and it's going to go off towards negative infinity as it approaches those asymptotes. Similar for the secant function, you can say, well, we know that the secant function is going to have vertical asymptotes at pi over 2, 3 pi over 2, 5 pi over 2, and so forth, because the cosine function is 0 there. Whenever the cosine is 1, the secant is going to be 1. And the secant will approach infinity as x approaches any asymptote in that region. In this region where we have at pi, we know the cosine of pi is -1, so the secant of pi is -1. As you approach 3 pi over 2 from the left, or as you approach pi over 2 from the right in that area, you know your y value has to go off towards negative infinity because it's increasingly becoming 1 divided by an extremely small negative number, which is going to go off towards negative infinity in that direction. Now, similarly, I could think of the graphs of tangent and cotangent. Remember, tangent is just the graph of sine over cosine. So again, it's going to have vertical asymptotes whenever the cosine is equal to 0. That's at negative pi over 2, pi over 2, 3 pi over 2, 5 pi over 2, and so forth. Really, the only portion you really need is this right in the middle. You can say, well, between negative pi over 2 and pi over 2, it sort of looks like y equals x cubed stretched out between those two vertical asymptotes there. And then it's just going to have that exact same period cycle every pi radians after that. So unlike sine, cosine, secant, and cosecant, the period of the tangent and cotangent function is just going to be pi radians. They repeat themselves every pi radians. The cotangent, I've seen so many students that'll graph the cotangent, they'll graph it as if it's the negative of the tangent. It is not. Similar, you can say, well, it's not just the negative of the tangent, because your denominator is the sine of x. It's cotangent x over sine of x, which means it has completely different vertical asymptotes. It's being horizontally shifted pi over 2 radians to the right and then reflected. So you could think of, hey, well, the cotangent of x, it's equal to the negative of the tangent of x minus pi over 2 radians. That would be true. So you can say all you got to do is shift it over pi over 2 radians, reverse the direction. So we say it's going to have vertical asymptotes at 0, pi, 2 pi, negative pi, and it's going to start high, go through the x-axis right in between our two asymptotes, vertical asymptotes, and then go off towards negative infinity as it approaches the second one. But now, all of that should have been discussed in a trigonometry or precalculus class and needs to be committed to memory as far as becoming comfortable with those. As far as precalculus identities, if you know the ones that I put on this chart, you'll be in good shape. So the ones that are not listed here that I remember doing in the homework, there were some of the homework problems that involved double angle identities, like the sine of 2 theta is 2 sine theta cosine theta. The cosine of 2 theta is cosine squared theta minus sine squared theta. Is it great to know those two? Sure, but I'm just not saying you have to. But I am saying you have to know everything on this chart. So if you're not already familiar with the ones on this chart, please do commit those to memory. Remember, again, this is printed out in your notes. And you can pull up this last page and just hopefully commit it to memory. Most people already know the reciprocal identities. The quotient identities go along with that. The Pythagorean identity, sine squared plus cosine squared is equal to 1, 1 plus tangent squared is secant squared, and 1 plus cotangent squared is cosecant squared, all very useful. I'm not as interested in these, but they will come up, usually actually more so in Calc 2 than they do in Calc 1. They're not as helpful for us in this class. All right, guys, that will finish it for this section. Please do remember, I'm not saying that everything in this video is going to answer all of your homework questions. That was not the intent. There's no possible way to do one video to cover everything you should know from a pre-calculus class. However, this tried to hit the highlights, and remember, any problem that you can't do on Achieve in the homework, I've done a homework video of me working out every single one of those problems, which should be of help. But in any event, if there is any questions, please feel free to always contact me. I'm here to help.